Hi, I'm Huiyu. I'm going to introduce our work, VisFusion, Visibility-Aware Online 3D Scene Reconstruction from Videos. Given the RGB video with camera poses, our goal is to achieve online 3D scene reconstruction. Previous methods use multi-view features either by averaging or tension, which cannot explicitly model the visibility. In addition, they specify the volume with a fixed threshold that tends to remove scene structures at coarse layer. In this paper, we propose a new pipeline to solve these problems. For feature fusion, we predict the visibility weights for all views based on the similarity maps of features. The key insight is that photometric consistency between multi-view features provides strong heuristics for view selection. For sparsification, we propose to specify voxels along the visual rays to keep more detailed structures. Our method achieves more complete and detailed reconstruction. Now we look at this work in more detail. Most previous works adopt a two-stage pipeline, that they first estimate the depth maps for each keyframe image and then fuses them into a 3D TSDF volume. However, they struggle to produce coherent 3D surface, especially for the textureless regions like the walls, because each depth is estimated separately. Alternatively, recent works adopt a volumetric feature fusion pipeline. They have two key components. The first one is a local-to-global feature fusion to achieve globally consistent reconstruction, and the second one is a volume sparsification from coarse to fine to save memory consumption. However, in the local feature fusion, these methods aggregate multi-view features either by simply averaging them that completely ignore the occlusion problem in the scene, or apply the attention mechanism, which implicitly model the visibility without explicit supervision, and has to select at least one view for the empty voxels due to the normalization layers. In addition, their sparsification relies on a fixed threshold, which tends to remove scene structures at coarse layer. Furthermore, they directly regress the TSDF at each level, without considering the relationship of TSDF predictions between different layers. Therefore, these limitations motivated our solutions that to apply a visibility-aware local feature fusion, array-based volume sparsification, and the residual learning of TSDF prediction from coarse to fine. Here is the overview of our coarse to fine pipeline. Given several keyframe images, we extract features from input images and then back-project these features into the 3D space to build a local feature volume with different resolutions. For each voxel, we use the visibility weights to aggregate multi-view features instead of treating them equally. We define a voxel to be visible to a camera view if it is on object surface and not be occluded. Our key insight is that the photometric consistency between features from different views should provide strong heuristics for view selection. Here the red dot is a surface voxel that occupied by the bag on the floor. It is only visible in the last 5 views. From the similarity map, we can find the features extracted from visible views have higher similarity with each other than those from invisible views. For the unoccupied empty voxel in the air, like the green cross in the images, the features from all the input views have low similarity value with each other. Based on this observation, we propose to infer the visibility weights for each view of each voxel from the similarity map to better deal with the occlusion problem. By doing this, we could explicitly supervise the visibility learning and reject invisible views by assigning a near-zero fusion weight to these views. Specifically, in the local feature fusion module, for each voxel, given the features extracted from different views, we first compute their pairwise cosine similarities to get the similarity map, and then use the 3D convolutional neural network to produce the visibility weights. The multi-view features are aggregated by these visibility weights, and then fed into another 3D CNN followed by an MLP to obtain the local occupancy and TSDF for our array-based sparsification. The training loss of our visibility is the L2 loss of the ground truth and the predicted visibility weights. The occupancy loss is the binary cross entropy loss of the ground truth and the predicted occupancy, and the TSDF loss is the L1 loss on the log transform TSDF estimations. Then we use the predicted local occupancy to specify the feature volume. Instead of relying on a fixed global threshold, we propose to specify along visual rays, which guarantee at least one voxel is preserved for each ray. Our key insight is that the voxel containing a thin structure should have a higher occupancy probability among voxels along the visual ray. Specifically, for each pixel in the image, we cast a ray from this pixel to get the voxels this ray passes and their local occupancies. We obtain a set of sliding windows, each of which covers several consecutive voxels. The sliding window with the highest sum of occupancies computed from covered voxels is preserved for the next level. Then a GRU module is applied to fuse the local features to global one and use an MLP to regress the TSDF at coarse level. At fine levels, instead of regress the TSDF directly, we upsample the TSDF from coarse level and learn the residual to achieve better TSDF prediction. Finally, we save the predicted TSDF into the global map to achieve online updating. Experiments demonstrate that our methods reconstruct the scene with more complete surface and fine details. On the ScanNet dataset, compared with previous online feature fusion methods, our method performed the best in the chamfer metric. More results and the source code are available on our project page. Thanks for your watching.